SwayamPrabha. Digital India. Educated India.
Okay, good morning. And so we learn wave energy converter, right? First, we learn the vibration, we learn the wave dynamics, we learn the wave and structure interaction. Based on wave and structure interaction, we know the modeling. Okay, today we are going to learn two things. One is wave energy converter, how to optimize this parameter, right? In what kind of case you get maximum power. Okay, so second part, we talk about 2-degree freedom vibration system and 2-degree freedom wave energy converter. Okay, and this is, so far I have to highlight, this is mechanical power, how much power we absorb, right? And the next Monday we are going to also learn output power. Output power is a little bit more complicated. We need to consider the certain efficiency. So today we are going to talk about wave energy converter power and optimization. Okay, and then this is lecture 7. Lecture 8 is about wave energy converter in 2-degree freedom system. So we learned that yesterday for the modeling, this is the frequency domain. What I mean, x equal amplitude EGI or I omega t, right? And here we get a concept of added mass. This is frequency dependent, radiation damping frequency dependent, and also excitation force that is frequency dependent. And also we learned hydrostatic stiffness that is proportional to the water surface area or water line surface area, right? So then for these three frequency dependent parameter, including added mass, radiation damping, and excitation force, we can use a potential flow like Watt, Kaplan, and Nemo to calculate. NCERT also can calculate. And then we also talk about time domain modeling. In this time domain modeling, there are two types of version. Okay, and some people, most of the literature, they assume the force excitation. For the given force excitation, the radiation damping can be calculated using Cummings equation, in which the frequency dependent damping using this way to calculate the impulse response. The physical meaning of this impulse response is given the velocity input, okay, pulse. Then you calculate how much radiation force. Okay, so another version is using displacement input, right? In which you can use a convolution term to calculate the excitation force. Okay, so here I put it this way: if your calculated excitation force is normalized based on wave amplitude, right? Here you need to type wave amplitude in this place. I didn't put here. You remember the calculation can be amplitude dependent, right? Normalized, last lecture use gamma, right? F divided by the gamma equal force divided by amplitude, right? If you have gamma here, this you time the amplitude in that frequency. Okay, so we also learned that we can use time domain simulation like WEC, and the software is for free. You can download. There are a lot of nice YouTube video, and the developers in National Renewable Energy Lab and Sandia National Lab put online. Okay, so now we look into wave power, right? So you think about wave energy converter. There are three figures, right? You move up and down, and then you have PTO damping and PTO stiffness. Now you look at here how you implement. Then you may put this on the seabed. You have floater buoy move up and down. When floater buoy move up and down, then you drive a ball screw, right? And ball screw drive a generator. That is one way to implement that. If you look into that configuration, you will find the force. Okay, excitation force, there are additional term, rotation inertia, right? And because ball screw, there's a rotation inertia, and how large the force generated, there are three terms. One is you may have additional PTO stiffness. You may, I say may, I'm going to discuss in most cases we don't. Okay, and you may have PTO damping, right? And in the second lecture, we learned if you have a generator, you short the generator as a resistor, it acts as a damper, right? That is electric damping, PTO damping. A third term is rotation inertia, right? And if you have rotation inertia and time acceleration, that's the force, because the generator, the ball screw, the transmission, that's rotation inertia. Okay, so ideally, this system is written in that way. Put here, you have wave input, you have mass, you have physical mass, and physical mass we use 3. That means is 3z direction. Okay, this 3. Okay, and then here you have PTO force. Now you write equation, vibration equation here, and spring, this spring damping mass, excitation force, right? And this 3 means z direction again. And now the mass, you have physical mass here, you have added mass, right? We explain what the added mass mean. The water surrounding mass is moving. There's energy or there's a force. Okay, so another thing is PTO, there's mass here. Okay, now the damping term, there are PTO damping, right? As I mentioned, you short the circle, it generates a damping effect. And you may have radiation damping, we put C33 here. Okay, now you have K33, that's hydrostatic stiffness. Then that is PTO stiffness. Okay, so using this equation, we can calculate the motion, right? If your force is given in this harmonic form, that is amplitude, right? Then the buoy, that is x amplitude, right? So now you plug this x dot, x double dot in this way, put in this equation. You can calculate the amplitude. I skip that. Okay, again, you put this here, right? And put velocity here, put this here, right? Then Ej omega t or I omega t all cancelled. Now you calculate the amplitude. This wave buoy, the amplitude, it depends on the parameter, right? Including the mass per meter and damping per meter, stiffness per meter. Okay. Now with this in mind, we can calculate the power, right? Power, that is average power, okay, is proportional to the damping coefficient, the PTO damping coefficient or electric damping coefficient. It is proportional to the relative velocity, right? Velocity is omega square times x amplitude square, that is velocity square, right? So that is the average power. You can calculate the power equal damping force time velocity, where damping force is C PTO time x dot, then time x dot. This is why x dot come here, okay? And x dot become omega time x. Okay, so you already get this amplitude here. You plug this expression, you get vibration power, how much power you can harvest. Now, how much power we can harvest, how to get the maximum power. Okay, so I rewrite the equation here, and I write that optimization, I sub-optimization, I tell you why. Okay, so let us say a simplified case, right? Suppose you have some system that you can ignore the moving mass, right? And that type of thing can be true. For example, you put a voice coil motor here, and the direct voice coil mass is very small compared with the PTO mass. In such kind of case, you take MPTO as 0. Another thing is, if you shunt this motor as resistor, you have damping naturally, but where's the stiffness, right? And if you shunt that as motor, you don't have stiffness. Therefore, most case, in such a kind of case, the PTO stiffness is 0. Okay, I say most case, right? Because the shunt that is, it has a resistor effect. And if you implement active control, then you can have positive stiffness, negative stiffness. Let us say suboptimal system in which we only optimize the PTO damping, right? PTO damping, how to optimize the PTO damping? You shunt the motor with different resistor, right? This is one way to achieve PTO damping. Okay, another way to achieve PTO damping, you may have power electronics that convert such kind of energy into DC or into useful energy stored in battery. In such a kind of case, the PTO damping is achieved through power electronics. Okay, and now you already understand the PTO is shunt as a resistor, you have ideal damping. This ideal damping can be achieved using energy storage element 2. That is battery plus power, power electronics. Okay, or better, you may not have battery. You may have power electronics plus inverter plus grid, and that also have input impedance to this system will be output impedance to this system. Anyway, let us say the suboptimal system. What's the best damping for here? Okay, and what's the best damping? Okay, let us simplify this expression. Like here, you have MPTO is 0, right? And KPTO is 0. And in such kind of case, the average power can be simplified here. Okay, so they have M omega square. That's the force excitation amplitude square. Say PTO here, right? This is numerator, you have PTO, right? Denominator, you can say you also have PTO here, right? This is why at the beginning of class I say, okay, and look like the PTO, we want to have large C, right? However, you have large C here, you may have small amplitude. So you have C show up in the numeric term and denominator term. Okay, now let us define the natural frequency of system. Again, this natural frequency will depend on the added mass, physical mass, as well as hydrostatic stiffness. Okay, that is natural frequency. Now, can you guys tell me how to choose the best damping given the expression here? So now you can do that way, dP, dC, PTO, to make this 0, then you maximize the power, right? So in such a kind of case, you will say dP, dC, you have this expression. Okay, this expression to be 0, you will find, well, okay, just say PTO equal our radiation damping. So in such a kind of case, you have maximum power output, right? So how much is the power? You take the C PTO equal C radiation damping into the expression, so you get maximum power in that way. Okay, so maximum power is the force divided by damping here, divided by 8. Okay, so now this expression is very important. Okay, and you get sense. Okay, now if I want to have maximum power, what we should do? Reduce radiation damping, right? You can reduce radiation damping by half. You can double the power output, right? Therefore, this is why we talk about several designs how to reduce the damping. So this is suboptimal. Suboptimal means we pre-assume that K PTO and PTO will be 0. Okay, and so now given this idea damping case, PTO damping equal radiation damping, you can calculate the amplitude of vibration system. Amplitude of the vibration system, you just put the expression here, right? And then let me see that one. So you give this parameter to here, you can get the PTO damping. PTO's the buoy's amplitude. Okay, so it's proportional to the excitation force, inverse proportional to the C33, right? And so in such kind of case, you reduce C33, which is the radiation damping. What do you have? You increase the vibration amplitude, right? So now look at the first equation. You reduce the radiation damping by half, you can have double the power output, right? Meanwhile, you reduce the radiation damping by half, then vibration amplitude get doubled. Okay. So this is a wave energy converter, how you choose the best damping. Okay. So let's give a case study. Okay. Get sense. Okay. So and our buoy put in the water is a ball shape, right? And the ball shape now, and suppose this ball is half submerged, half in the air, right? And so for this one, you can calculate the physical mass, right? And suppose physical mass you use water density, you can calculate the physical mass because your ball is half in the water, right? So physical mass you can write it that way. Now you have added mass. Added mass here, that is half the ball volume, the half the displaced the water, right? So now you have added mass, you have physical mass, then you can calculate the natural frequency. Okay, so now hydrostatic stiffness is rho g times pi r square. Pi r square is cross-section area. Okay, now you plug this into here. What you have here, the natural frequency is g divided by r. This expression is very, very simple, right? You have ball in the system, you half submerged. So your natural frequency, G divided by R. Okay, so what does that mean? Okay, if you have smaller ball, natural frequency usually is higher. This I explained today, right? So we want to say, if we want to have resonance happen, what kind of ball size need to be? Okay. So let us say that way. Okay, typically ocean, right, 4 to 16 seconds, and it depends, right? If very, very close to the ocean is 4 seconds, right, wave period. Okay, and in United States East Coast, let us say typically 6 to 8 seconds, and West Coast is higher, 8 to 10 seconds. Okay, so let us say now, if you know this period of wave frequency, wave period, right, you can calculate the frequency omega, right? Omega is 1 over pi divided by t, right? So then you can get that is about 0.4 to 1.6 radius per second. So now let us say you want to match, create a resonance for 16 seconds wave, then your diameter ball is 66 meter, or your radius, the 66 radius Okay, is radius, not diameter. Diameter times 2, 132 meters. 132 meters, in that way you can have resonance, right? If your wave period is 4 seconds, right, you can calculate that your bore size need to 8 meters, right? And you just imagine that way, if you build some wave energy converter around the Indian Ocean, very likely you have maybe 7 seconds, whatever like that, then you have big bore size. This is not practical, right? So, as I mentioned to you, if bore size is too large, then it's just rock, right? It wouldn't move. Okay, so, 832 meters, this is too high, right? Typically what happens is bore size is small. If bore size is small, then the wave frequency is small. Okay, let's see what we can do, right? And as we say, wow, it's really hard to achieve such kind of resonance frequency. So don't forget that now come to this system again, they have PTO force, where there are 3 components. Damping, we only take advantage of damping. We didn't take advantage of K or PTO, right? So what you can do? You can take advantage of stiffness. You can take advantage of the rotation inertia. Okay, so let us first take a look at how to take advantage of rotation inertia. Okay, and now if this is not 0, suppose we have small bore, 5 meters diameter. Okay, so now you still have this expression, right? Just now we say when we do the suboptimal, we assume Z2 will be 0. Now Z2 is not 0. You can calculate the CPTO, the expression in that way, right? Then you can write the average power output is similar. The only thing is the expression side, in addition to the PTO's damping term, you also have PTO's stiffness term, PTO's this stiffness term, PTO's mass term, right? Now you can take advantage of these parameters, right, to get better performance. Let us say. We write the expression here, right? And I mentioned that the natural frequency, usually the buoy, smaller buoy, the natural frequency too low. Take a look at the natural frequency here, right? Natural frequency, there's hydrostatic stiffness here, PTO stiffness here, right? Then you have physical mass, added mass, PTO mass. So you want to reduce such a natural frequency. Okay, and you want to have resonance. Resonance in that way, typically this is too natural frequency too high, right? And natural frequency too high, you want to let me see, I got confused myself. Okay, natural frequency too high, you want to reduce that. Reduce that, you want to make a numerator part small, denominator part large, right? You want a small, you just make K or 0. What if you can make K test stiffness, negative stiffness, right? You can use control to achieve negative stiffness, right? Suppose you don't want to use active control. You want to, just use the passive. Now, stiffness, you just make it 0. Okay, you don't put a spring, damper, whatever spring here. You can put a spring here, right? And spring is their stiffness. Now you assume make it numerator small. Now it's 0. You want to make this large. Okay, so want to make this large. Okay, in that way you achieve the natural frequency. If you want to achieve natural frequency, then use large PTO rotation inertia. Rotation inertia and the transmission ratio rate of the mass. Okay, so that is how much rotation inertia you need to achieve the resonance. I stop here for a moment. Now you understand what we try to do. We try to achieve resonance. We achieve resonance now for small buoy. If you only have added mass and fixed mass, this natural frequency is very, very high, right? We want to reduce this natural frequency to achieve the resonance, right? And the day before yesterday, we talked about use fixed mass and added mass to achieve resonance. Today, I said, okay, in addition to use added mass, we can use PTO's mass. And you remember, I have a figure to show the cup shape, right? Cup side, you have added mass. This added mass, you can reduce the frequency. Now, I'm teaching you another way to reduce the frequency. You put the flying wheel on the generator. Is this clear? You put a flying wheel on the generator, you have larger rotation inertia. Larger rotation inertia, as a result, you have large PTO mass. Right? If the PTO mass follow this formula, then you achieve resonance. Okay, so this is a theoretical case. Let us say how much mass we need. So, and I'm going to give an example after this. I tell you, okay, how much mass we need. Okay, so now, what's the physical meaning? Okay, and physical meaning is here. We still write the equation here, right? Mass, damping, stiffness, excitation, force. So, and if everything is harmonic, right? Everything is harmonic. X equal capital X times Ej omega t, right? Ej omega t. Okay, we write everything in the force, right? And this j omega time. Let me say that way. If this time velocity was that, this time velocity what this will be? Damping force, right? So then if this time velocity, this is inertial force, right? If this time velocity, what do you have? That is stiffness force. They have j omega here, you have 1 over j omega here, damping force. This is the angle, right? So basically, the damping force is perpendicular to the inertial force, right? Inertial force and stiffness force is out of phase. You can write this expression. This is k, another is omega square times m, right? Therefore, this is out of phase. Okay, what we try to do here? Okay, and you want this cancel together. Basically, you meet this equation. When you meet this equation, omega meets this equation, the stiffness force and the mass force added together will be 0. Right? Then the rest added together will be damping force. Okay, and the damping force, if stiffness and mass cancelled, then total force left side will be damping force. Okay, in that way, the excitation force and damping force will be in same direction. In that way, every time you give excitation to the buoy, whatever, this force always in the same direction as your damping force. So every step, every time you pump energy to the system, right, the energy is taken away by this damping force. In that way, you have maximum power input to the buoy. So the first very, very intuitive goal is you achieve the system so that the input force will be always proportional to your velocity direction. This is very intuitive, right? You have this buoy move up and down. Every time you give force, it's the same direction. In that way, you have maximum input power to the system. That is the physical meaning. Okay, now physical meaning we talk or not. Okay, we said last time we use the cup shape to add added mass. The purpose is cancel the stiffness, right? Then you can add or rotation inertia flying wheel. You also cancel the stiffness, right? Sometimes you cannot cancel the stiffness. Okay, I use a negative stiffness through control. Then I try to reduce the stiffness force so that I can cancel the mass effect. So everything look into this equation, right? You write in frequency domain, and in frequency domain here, that is single frequency, x equal capital X times e j omega t, right? So in that way, we want to cancel this effect of stiffness and mass, and so that the force direction and the velocity direction is always in phase. So wave energy converter is pretty easy, right? You just design your system, no matter your added mass design, no matter your flying wheel design, or stiffness choose. You want to achieve such kind of thing, the force, spring force, and inertial force cancelled, then the damping force and excitation force in phase.